Okay. I don't know why it's cutting off on the bottom because of that program I'm using to capture the screen, but you all have this in your notes, so you can kind of. But if you look at some data, this is some real data, some real NIRS data, and you see, if you zoomed in here, you'd probably see a little bit of cardiac, but you see these slow drifts through the data. And if you look at the autocorrelation of that, that is, you take say the current time point, and you ask, can that time point be predicted by the point one before, and the point one before, and the point one? So it turns out that its history is very informative to the current time point. And if you look at this is it's 20 hertz. You have to go out to 600 points in the past, which is 30 seconds in your history before you actually get a statistically independent point again, right? Which means that our data are not independent. We might have 1,000 measurements of data, but we don't have nearly 1,000 degrees of freedom in terms of our actual measurement. And so, again, we're going to see that this has a huge effect on false discovery rates if we don't take it into account in our NIRS data. Okay. Again, this is also true in both the time domain, but also the spatial domain. When we think about the effect of, say, superficial physiology and blood pressure, it's the whole probe going like this, right? You've got this oscillation across the entire head. It's a very global signal. So not only are our noise structures correlated in time, they're also correlated in space as well. And so our channels spatially become non-independent. We can also take that a step farther and say that oxy and deoxyhemoglobin were driven by this common underlying neural process. So those themselves are not actually independent measures either. Oxy goes up, deoxy goes down. That's our expected response. They're not independent measures there. So we're going to deal with that and how the statistics change for that. And let me just finish this last one, and then I'll get the question in the back. The last assumption we make is the assumption of stationarity, which is that our noise structures are constant over time. This is hopefully true in most NIRS studies because we don't have really good ways to deal with it. I'm going to show in our toolboxes, we deal with all of this up here. We have nice statistical methods to deal with all this. This one still causes a little bit of issue. There's not really great ways to deal with the kind of non-stationarities we see in NIRS. But an example of this, which will come back in Hendrik's talk tomorrow, is superficial physiology when it's linked to the task. So if you tap your fingers, start tapping your fingers in a block design, what happens is your heart rate probably went up each time you tap your fingers. If it was short enough, you probably held your breath while you did it. And what happens is over several blocks of repeated pattern, your physiology actually starts to phase lock with the task. So what you'll typically see is like your Mayer waves, this 1 over 10 second type oscillation, will actually start to couple in with your task or the finger tapping. And so this creates a non-stationarity in terms of the noise structures and so on. For those in the audience that are doing gait studies and walking and stuff like that, your heart rate is going to be much higher during the walking task than it is during a standing or seated task. Seated is going to be very different physiology in terms of your blood pressure oscillations compared to standing, right? So you've got these issues of non-stationarity in the noise, and it's at the moment, as I said, it's stuff that we're kind of working on ways to deal with. You'll see when Hendrik's talk a little bit of short separation to try to remove some of this, but we don't have, this one is not fully solved yet. These are reasonably under control. Okay, so before we go into how we put those under control, you got a question? Is it still applicable? Yeah. Yes. So if you just so you're computing it. The way I explain it is you take your current time point and you look in the past, but you do that for every possible current time point. And it's basically what you do is you set up a linear regression in which your data, which is the y vector, is modeled as shifts of its own history. and then you solve for those shift coefficients. We'll see the equation in a little bit. Any other questions? So I will go for maybe 15 more minutes on this, and I'll stop. We can break for coffee and so on at 10:30. That puts us back on schedule, and then I'll resume this stuff, okay? So that'll bring me through most of Jeff's code. Okay. So dealing with these issues of kind of non-ideal noise. So there's three ways that we can deal with this. So historically, this has been the one that the NIRS field has used, this idea of pre-filtering. It's what's used in the Homer 2 programs. It's what most people have used to date in the publication. And the idea of pre-filtering is, an example of it is bandpass filtering. Right? I have cardiac, I have respiratory oscillations. Cardiac I can remove because I can do a low-pass filter, throws out all that cardiac signal at 1 hertz, and then keeps my signal of interest, which I believe to be all less than 1 hertz. Right? So you can apply a filter like bandpass filtering to your data to try to remove some of the features of the noise that you're trying to get rid of. In pre-filtering, if you think about this equation, y equals x times beta, pre-filtering is actually only applied to the left side of this equation. Right? We only apply it to the data itself, which means that if we're not careful about the design of the filter, you can actually alter the estimate of the random. So say, for example, I'm doing a finger tapping pass. Tap my fingers for 10 seconds, wait for 10 seconds, tap again. I've kind of got a natural frequency of about 1/20th, right? So if I use a low pass, or let's say if I use a high pass filter, right, which is going to let anything, which is going to kill anything slower than the high pass, the pass band, and let the faster frequencies go. I have to choose my high pass filter to be low enough such that it's going to kill slow drift, but it's not going to interfere with this 1/20, right? So I'd have to choose a low pass filter that's say 1/60 or something like that, that's going to kill slow drifts that take a minute or longer to evolve, but it's going to leave this 20-second period intact. So you have to be careful with pre-filtering. You're making assumptions when you do pre-filtering that what you're removing only existed on this side of the equation, and there was nothing in your task that actually represented, or your signal of interest, let's say, that represented that frequency. Yeah, Ben.
If you're going to collect these over feel free to comment, but since you used the example of 1/60 for the low pass,
yeah.
Is there any danger from harmonics of the task frequency?
Yeah. Yeah.
So is it better to use an older 1/60, or does it make no difference to do a 1/70?
Let me get through the next two, because the answer to that question is don't pre-filter. All right. So you're making prior assumptions about the structure of the noise that may or may not be true for your data. The motion correction stuff is also a form of pre-filtering. Pre-filtering to be applied to this side. And so if you were, say, using motion correction to remove the artifacts, you're assuming that your motion correction is perfect, right? Because after it gets done, then I'm still going to do stats on this. I'm going to assume that I've gotten rid of all those outliers, right? So if your filter is not optimally designed, if it's applied to the data, but there's still something left in the filtered noise that still violates your assumption, it's going to be less bad than it was, but it's still going to be not great. Okay, so you have to be careful with pre-filtering that you've applied the right filter, that it hasn't distorted the estimate of beta in some way, and you did it in a perfect sense, and you actually ended up with ideal noise at the end, which is, needless to say, kind of hard to hit all of those points on. Yeah. Yeah. Yeah, we're going to return to that, but the answer is yes. Let me return to that, because it's I'll return to that, but you're correct in that interpolation of what I said. So okay, so pre-filtering. Pre-filtering has historically been done in the NIRS community. I think that's probably the widest used method in EEG. The alternative, a alternative to that, is what's called pre-coloring. And so the problem with your noise in the NIRS data is not that you have these frequencies, this cardiac, this blood pressure. It's that you don't know what it is. And so if you knew what the colored structure actually was, you could then just go modify your degrees of freedom and correct your model that way. And so what pre-coloring does is it takes your underlying signal, your underlying noise, and imposes onto it a very, very strong but known colored signal. So what you do in pre-coloring, it can be done over space or time. Let's take the temporal example. So what you would do is you would apply a really strong low-pass filter to your data. But unlike pre-filtering, what you do is you apply it, sorry, it's down here. You apply it to both sides. You color both the data itself and the right-hand side of the equation, your design matrix. So that because you've applied it to both sides of the equation, in principle, data stays the same, in principle. And so now, though, when you look at this residual that's left over, it has structure that's been imposed by this pre-coloring stuff. And so because you know what structure you imposed on it, you can then correct your statistical model. So an example I always use, whether or not it's appropriate or not, is I'm writing a grant. It's the absolute best grant you've ever seen. It's this wonderful figure. Yeah, it's all colorful and so on. And then my 3-year-old daughter comes and draws over it with a blue crayon, right? And the question is, well, what color was the figure, right? Well, it's blue. No matter what color underlying was, you've colored it with such strong colored noise that it becomes blue, and to first order, you now know what it is, okay? So that's the idea of pre-coloring. However, a downside of pre-coloring, so pre-coloring, I will say, is if your errors are simply due to physiology and these serial correlations and this autocorrelation structure, pre-coloring works really, really well. Okay, it actually works even better than pre-whitening, which is the one it's widely used in fMRI and the NIRS SPM code, the SPM community. However, the downside of pre-coloring is that you're assuming that the structure that you impose is much, much stronger than the noise that was already in there. So now if we go to NIRS data where we have these really, really strong outliers, these motion artifacts, right? So now that figure that I was drawing had a really bright red spot. It was done in Sharpie marker. It was so dark that even though my daughter colored over in blue, you can still see that red dot, right? Because it was such a strong outline. Same thing with a motion artifact. If I pre-color the motion data with a motion artifact, because that artifact was so strong, it still remains even after I pre-color. And in fact, actually, if you took data that has this spike or shift artifact, and you low-pass filtered it, you've now smeared it across the data, and you've actually made the structure even worse. So pre-coloring like this works really well for physiology, for getting rid of physiology, but if you have outliers, it actually makes it much worse. Okay? And with that, it's 10:30, so before we get to the last method of pre-whitening, which is what we do in our toolbox, and you'll see why it gets around these two issues, let's break for coffee, give myself a chance to stop talking, and then go from there, okay? No.
They like send you outside.
Yeah, because that one file we can open the file. Let's say you want to plug in.
So I think he was asked for yeah, I just did. I know, so that's true. He wouldn't let me. Like, no. Somebody else has it. So Carlos like subbed.
Maybe, yeah, maybe again.
So when I get back to routine,
Yeah. But
yeah, but you don't get yeah, exactly.
We'll get there. Okay. So I've heard there's a number of people having trouble with some of the demos. So in the demo script, it's like the first or second line, it says like folder equals, and it has a comment of like change this to match your computer, because you probably don't have a drive called users/Ted hopefully not on your computer, but something that effect. But if I think my suggestion was change that to match somewhere on your computer, and then you should be okay. Because I think most people are having this issue with make directory not having permissions, and it had to do with you didn't have a Ted Hubbard folder or whatever. So we're not going to handle that until after lunch. But if you're kind of behind the scenes playing with the toolbox, try that. If you still can't get help, we can ask one of myself or one of my students. All right. What was I going to say? Oh, and by the way, if you take the stairs to go up or down to the second floor, you need an ID badge to get back in. So hence I had to walk all the way around the building just now because my ID badge is in my backpack. Just be aware. Okay. So, back to this. So we talked about we have these issues of noise in our data. It has serial correlations, autocorrelated structures, colored noise, and these outliers. And pre-filtering is a good way to do it if you're confident that your filter is perfect, but oftentimes it's really hard to be that confident of that. Pre-coloring, we said, was really good for one of these things, for the physiology component, but actually if you had motion artifacts, made it worse. So now what we're going to do is we're going to talk about the alternative, which is called pre-whitening. And pre-whitening is it's kind of the opposite of pre-coloring. Which is, what you do is you take your data, from the data itself, you derive an optimal filter based on the autocorrelation structure. So you try to find the filter that's going to whiten all the frequencies of your data and result in white in a truly random normal distribution for the epsilon there. And then you take that filter and you apply it to both sides of the equation. So you go back, you find the optimal filter, and then you apply that filter to both the left-hand side where you're filtering the data, but also the right-hand side where you're filtering your design images. So just like the pre-coloring method, by applying it to both sides, in theory, data is fairly untouched. What you've done, though, is you've actually weighted certain parts of the data are more important than other parts of the data in terms of providing this white noise structure. Okay? And so this idea of pre-whitening, there's a couple ways you can do it, mostly with autoregressive models or ARMA or integrative ARMA models. And this is actually already done in programs like NIRS SPM or SPM for analysis. And we'll return to that in a second. So the way, and this was the question from earlier, So if you have data that looks like this, right? So you've got physiology, you've got then a spike artifact because the probe moved, and then maybe a shift artifact, the probe moved and came back to a different place, and then you've got this physiology still in here. So what you would do is you can take the data like this, you can model it with an autoregressive equation, which says that the current time point is modeled as a linear combination of its history. The number of terms back you go is the model order. So in this case, well, if I stop there, that would be model order 2, because I'm modeling the current point based on the 2 points from its history. So you've got the model order. And the higher the model order, the more parameters you have in your model, but the more structure you can start to model in your data. If you only had a pure sine wave, first order would be okay. If you don't have a pure sine wave, we have more complicated structure. Anyway, so you can design this. Basically, what you do is you set this up, you solve for these coefficients, rho, and then you take those coefficients and you can build a. I'm sorry, this is so low for those in the back, and you can't possibly see this, but you have the notes. But you can build a whitening filter by basically taking those autoregressive coefficients, right? And so if I take that whitening filter and I apply it to my data, what's going to happen is the data is going to, which just kind of went up. Okay. The data is going to go from here, we have physiology, to this blue curve here where it's now white, right? You still have these really strong motion artifacts in there. Actually, they're actually even more apparent because they stand out so much higher than the regular background of the noise, of the physiological noises. And if you look at the autocorrelation, this is again, how much should I depend on my previous history? In the original data, here at, let's make it up 10 hertz, so going back a couple seconds of data, predicts the current point, to roughly 99% of the information that's in the current point, right? And you really have to, we saw it in the previous example, you have to go back a really long time before you reach a truly independent measure. But after you've whitened, you've taken the data and you've applied this filter, now if you go back one step in time, you now have an independent measure, right? So that's this idea of the data being uncorrelated, so white, okay? Yeah, Miriam.
So if you have a bulk design,
No. I'll show how we do this. Okay. Yeah. 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 Well, this is an AR model. This is the AR model fit to this data, and there's clearly the baseline change. We're going to see that in a bit. So actually, I'll go second. So the in fMRI or NIRS SPM, the models that they use there, because of the way they solve them, are limited to first, maybe second order. You can't go much higher than that because of the way they actually solve it. It's modeled on more of a statistical method versus an actual autoregressive fit. Okay. So what happens is you're able to account for some of this noise, but not enough. fMRI first order model is perfectly fine because we only sample once every 2 seconds. So you only have to go back a couple time points before you actually reach an independent measure. But with NIRS, we're sampling at 10 hertz. So we have to go back a lot more time points before we're actually independent of that, right? So the model order in NIRS has to be much, much higher, right? So generally, what we do when we fit this, and I'll show this in maybe the next couple of slides, we use some sort of information criteria, and we tend to use AIC that figures the optimal model order, and then we use that to filter the data. Generally, that model order is on the order of maybe 15 to 20 for NIRS data, say like 4 hertz NIRS data. Anyway, so if you apply whitening, the idea is that you've created this unstructured random noise now. Yeah, Ben.
Which autoregressive model is actually implemented and doesn't have moving energy?
No, I only use AR, not an ARMA. And the answer to that is back to the model order. So you can, with a moving average model, you can get away with the moving average lets you use lower model order. However, it's really hard to do like BIC, AIC on the moving average problem, right? Whereas if you just use AR, you have to use a higher model order. But if you go high enough, it actually does the exact same thing as the MA part of it. So we prefer the AR because we can pull out those model selection techniques out of it. Okay? All right. So, yeah. Okay. So our recommendation, and again, this will probably make more sense after I go through, but our recommendation is definitely don't low-pass filter your data. High-pass filtering is okay, but low-pass filtering, what it's doing is actually imposing serial correlations on it. And so in that case, if you low-pass filter and then this is undoing the low-pass filter, you actually have to go to a higher model order to undo what you just did in the previous step. High-pass filter is a little bit different because it's actually killing these low frequencies, and so if you use high-pass with AR, you can use a lower model order then. But AR is it's the complete opposite of low-pass filtering, so you don't want to use those two together. Okay. Anyway, okay. So, and you all had complete valid questions because I haven't quite gotten to the end, the punchline of the story yet, and how we actually implement this. Okay. So let's just where we are right now. If you just took data like this, has physiology, has motion artifacts, and you apply an AR filter, you get rid of all of the structure of the physiology. But your motion artifacts here are still very apparent. In fact, they're actually more apparent. There are more outliers from that distribution. So this is what we call an innovations model. It's the after you're done whitening, it's the information that was added unique to each time point, right? That's not because it's not removed all the history. It's just the information added, injected into the system at that time point, the innovations. And so what we see is right here where there is this motion artifact. For some reason, there was a lot of information injected at that one time point. Same thing right here where we have that shift and so on. And so in the innovations model, baseline shifts or spikes in the data become really strong outliers compared to the white distribution. So again, if I do a histogram on this, these would be that heavy-tailed part of the distribution. So when we have data that has heavy tails like that, outliers, we can do methods like robust regression. What robust regression does, same thing as pre-whitening and pre-coloring, you apply a filter to both sides of the data. But the idea is this filter, S, is a weight of what is the probability of being an outlier. So these points that are nice, well distributed here, your weight goes to 1, I really want to include these. This guy who's 6 standard deviations away, he's definitely an outlier. And so this value of S varies from 0 to 1. 0 means I don't want to include you at all in the model. I'm going to take you out. You're an outlier. 1 is you're keeping everybody in. and so there's different ways to estimate S, but it's basically based on some sort of standardized residual of this 1 point is an outlier compared to everyone else. And the idea of those outliers, these guys that go down to 0, is you're zeroing them out in both the data and the design matrix. So effectively, it's actually just taking it out. That if you were such a strong outlier, it's solving the model without that term in. Okay. So let's put this all together. And actually, so the way that I jumped ahead of myself. I thought I had another slide in there. Okay. So the way that we solve this is what we do is it's an iterative process. So we first start off with our equation, y equals x times beta. This is our design matrix. So to Miriam's question about block design or something, that's encoded in the x part of this. Okay. So what we do is we first start off with no whitening and no robust regression. We solve this model, we get epsilon. From epsilon, we look at epsilon, oh, it's got all this physiology, it's got motion artifacts, it's the residual, those features were not modeled by this part of the design matrix, right? So what we do is we take epsilon and we fit epsilon to, we take the residual and we come up with a whitening filter based on it that's going to whiten this residual. We then go back to the original equation and we apply that whitening filter to both sides. Now when we solve it, epsilon has better qualities, right? So there's the for loop there that's looping over, iteratively updating, getting a better estimate of epsilon, and then getting a better estimate of the filter, and so on. Within that for loop, we also do the robust regression, which means that when we go and we try and solve this weighted or this whitened equation, we use what's called robust regression, which, just like that solving for that AR model, it solves for it, it figures out who's an outlier, and then iterates to downweight those outliers, right? So you've got these two nested for loops. One is doing the AR part, the pre-whitening. The other is doing the robust regression part. And so what ends up happening is you end up, after several repetitions of several loops through this, you end up with you've downweighted all of the outliers from the, that were high in the innovations, and you've removed all the physiology. And so now your estimate of, in theory, you've done everything, applying it to both sides of the equation, so beta, in theory, is kind of unchanged. In practice, it becomes less affected by motion artifacts and such, so it's not, it changes a little bit. But most importantly, your epsilon now has exactly the properties that you're looking for, that it's normally distributed, IID, and has no more of these heavy-tailed outliers. Okay? So now what happens is now, because my epsilon, my noise term, now fits my statistical assumptions, now when I go and I do that standardized t-test on whether or not beta was statistically non-zero, now I'm going to get a more accurate estimate, more accurate statistics. So let's see exactly what that does. Okay, so this was, as I said, this was all work that was done by Jeff Barker when he was a grad student in my lab. This was back in 2013. Hendrik, did we get this paper? Okay, so we gave 3 papers within the packet here. One is, it's called like commentary on the statistical properties of noise, and it's basically all what I just presented in a little bit more detail. But it was all derived from it was kind of a summary of this paper, basically. This is kind of a mathematical paper. We try to put it in more terms for more people to understand. And the other papers that are in there, there's a brand new paper that just came out last week on the NIRS toolbox, or the analyzer toolbox. I got used to saying that. But that's in there, and then there's another one on basically the statistical properties of resting state data. And we'll get to that one as well. Okay, so back to Jeff's paper. Okay, so so what Jeff did here was he took real experimental baseline data. This was data that was collected in children. So it definitely had physiology, but because it's children, it had motion artifacts too. So actually that example data that I kept showing that has the spike and the shift, that was one channel of data from this data set. And so what you do is you take that baseline data that has no activity in it, and you simulate brain activity on half of the channels. Or you take half the data, you simulate brain activity on it at a specific signal to noise. You then go and solve your model, and you look at the false positive, sensitivity specificity. You look at the channels that I simulated this activity on. Did I find it on those channels? The ones that were null, did I not find activity? So you can get an estimate of false positive, false negative. And you run this through thousands and thousands of times and generate a ROC curve. Receiver operator curve, which is what we're looking at here. So this is a ROC curve. This is the false positive rate versus the true positive rate. Random guessing is along the diagonal. A perfect model is up here at the left-hand corner, where you always got it right and never got it wrong. So you want to be up in that corner, right? And this depends. These curves depend a little bit on signal to noise, but the relative these were all generated at the same signal to noise. So if we take data that has no motion artifacts in it, so just has physiology, it doesn't have any motion artifacts. This is basically, we're looking at ordinary least squares, which is kind of the standard regression. And AR1, which is, we have a first order autoregressive model, and then an Mth order, where we solve for the optimal model through something like BFC. And I would say BFC then becomes the third nested for the treatment. That's a different thing. Okay, so if we just have physiology, our rock curves actually look almost identical, right, in terms of sensitivity, specificity. However, if we look at down here, this is a plot of, this is basically the x-axis is what MATLAB told me the p-value should have been, like based on that theory of, you know, studentized t-test assuming IID noise and so on, which we know was not true, versus what was the true false positive rate as determined from these simulations. So I ran 1,000 simulations, null simulations. How many of them came out as false positives at 0.05? I would expect 5% of it. But the answer is at 0.05 here, if you're doing ordinary least squares, it's closer to 40. 40% of the channels that you did not simulate activity on showed up significant at 0.05 threshold, right? And that's because that stat, that number 0.05, was based on these assumptions of this statistical model. It assumed you had 1,000 degrees of freedom, and you didn't come close to that because of these noise structures, because of these outliers, and so on. This data only has the noise, so it only has the physiology. We haven't talked about the outliers yet. If you have an AR1 model, you do a lot, and you do better, right? You're able to account for that history. You're able to get back, sort of independent measures. So you come down, it's not nearly as bad. Maybe it's 20% instead of 40% with an AR1. But if you actually start getting a higher and higher model order that's optimally determined, you can get back to this perfect curve where what MATLAB tells you is exactly what it comes out to be. So out of those 1,000 simulations, on average, 5% of them are false positives, which is acceptable as control type. Okay. If we look at the effect of spike or shift artifacts, now if we start to throw motion artifacts in, our sensitivity specificity curves start to suffer. So while they were all doing okay for just physiology in terms of rock curves, as soon as we start to throw motion artifacts in, we're starting to lose sensitivity. We're pulling the area of the curve is much lower. But so in this case, the blue curve, which is our algorithm, we're use it whether or not you have motion artifacts, regardless of the type of motion artifact, and it still gives roughly the same area under the curve. And again, to these false positives, the control of type 1 error, you still have in the ordinarily squares a huge false positive rate. If you go to the AR models, you control it. Here, it's actually going slightly below the curve, which means we're actually under-reporting our stats. We're being more conservative. But I always prefer to be more conservative than to publish something in Nature and then have to retract it the next week. All right, so that's this is the method that we're promoting within the toolbox. And the idea is, back to like Ben's question and stuff like that about what kind of pre-processing or what kind of motion correction we do, and I said I don't use motion correction, is there's two problems with motion. One is it's noise and it's bad, and if you had less noise, you would have better effect sizes and you'd have better data to be able to see with smaller sample size. But the other issue is that motion artifacts violates these statistical assumptions and does really bad things to the false positive rate. Okay, we fixed the false positive rates and so on in the area, the rock curves. You still have noise. That is, a data set with motion is still going to be less powered than a data set without motion, right? But so in that sense, if you went and, in addition to this, did something to reduce that motion artifact, and then got the stats right on top of it, you will do even better. Your rock curve will be even it'll affect the rock curve in terms of sensitivity, specificity. It'll make it a little bit better, provided your algorithm actually work right. It shouldn't do anything with the type 1 control. MATLAB should still be recording p-values correct. So these statistical methods are not independent of some of those pre-processing steps. You can still do them. But what we've found is actually that this method of kind of statistical correction, we kind of feel it should always be done, even if you do like a pre-processing step of motion correction. And if you start to look at start to examine real data, what you find is a lot of the issues that why we developed the motion algorithms in the first place in the physiology, because we were seeing these data that just didn't look right, these responses that did not look physiological because they were driven by motion artifacts. We don't see that nearly as much. We don't see nearly as much global signals using these statistical methods compared to the 40% false positive rate we had with the ordinary least squares. So what we've kind of found is data that previously we'd been kind of pre-processing and trying to figure out and so on. Once we got the stats right, we realized it actually wasn't nearly as bad of a problem as we thought it was. And so we're just now starting to go back of like, oh, okay, well, let's see if we can add motion artifact, does it indeed make it a little bit better than this? But the huge gain was actually by doing the statistics, such that for most data sets we don't do any additional pre-processing. Yes?
So, what clarification, so IWNS is the robust regression?
Yeah, so this is autoregressive, so P order autoregressive model with iterative weighted least squares. We got to have a better algorithm for that because it's terrible to keep writing out. But so when we talk about like the general linear model, right? The general part of that was referring to this idea of generalizing your statistics to deal with these non-ideal conditions, the serial correlations, the outliers, and stuff like that. And so that's what the GLM has implemented in programs like SVM and stuff do. The argument that I'm making is that the generalizations that we use for fMRI are not the same generalizations as we would need to use for NIRS, because our data is different. Our data is at a much higher sample rate. Our motion artifacts appear differently. So it's still the same idea of generalizing the model. It's just a different set of generalizations.
So in case of conventional fMRI, we also put up respiratory and pulse signals, and we also put motion regressors.
Yeah.
So what's your thought on that?
Well, so you'll see that again. Kind of, there's two issues. One is, well, motion is a little bit different because an fMRI motion is very different than fMRI or NIRS motion. But the physiology one, we'll see it in Hendrik's talk tomorrow because he's going to talk about some of the stuff we've started to do with short separation regression to clean out physiology. And it's the same idea. If you get the stats right, you're fine without doing that. If you do it, your area under the curve and the rock curve becomes better because you've lowered the noise because you've removed some of it. So it does help to do those methods in addition to this. And what you will see, I don't want to give away Hendrik's stuff, but we looked at all the different ways people have proposed to do short separation. And it turns out if you're only doing one thing, do the statistical method. If you're willing to do two things, it's put in a short distance regressor and do the statistical method, and then that's the best thing to do. Okay? So, yeah.
I had a question about, we talked about the weighting, and so if motion so happens that it's associated with a specific experimental condition, so because MRI, that's the issue with the spiking, and if there's fewer cells or that that's related. So I was just wondering about this method.
Yes. So again, it's first off, it's the effect of the motion artifact statistically is because it's an outlier. So we're down-weighting outliers. So if you have, let's say, a motion artifact that's not a spike, it's kind of a slow drift, of the probe. It's a motion artifact, but it wasn't actually affecting you statistically in terms of the false positive. So the algorithm doesn't correct. It's not going to downweight those because it's not actually an outlier, but it didn't need to because it wasn't violating the statistical assumptions. That made sense. To your question though, what about task-driven physiology or motion artifacts? So yeah, if you run this, you're going to, let's say, where's Kristen with her? Back there. Okay, so she's doing a task. It's spoken language with NIRS. Spoken language is incredibly hard to do with NIRS because you're measuring in the language areas and you have the mastoid muscles going up right over those. And every time you talk, it generates a huge signal that you believe is, the greatest brain activity ever, and it was actually just the muscle that you're recording. You have the same issue in fMRI. And so that's a task-driven motion artifact. And so if you use Outrun like this, what it's going to do, because motion artifacts were mostly in the task, it's going to downweight those, right? So you're going to lose power to do the detection of brain activity. Which means that you're going to, let's say, have a lot of type 2 error, right? In that you fail to see things. You have a lot of false negatives. But I definitely prefer type 2 error to type 1 in the sense that I'd rather have more subjects and to increase my power rather than falsely reporting results, right? I know, but that also gets at the to this statement of generalizing the model. This, and that's what I said a few times at the beginning, this stuff is generalizing it to motion artifacts and physiology. It's not generalizing to that third item, which was non-stationary noise. And what you're actually talking about is non-stationary noise. And that's a problem, and I don't have a good solution for that. Right, so, yeah. Any other questions before I move on? Oh, so no other questions? Okay, so ultimately, we have a model that went from y equals x times beta plus epsilon to a model that looks like this, where we have both the weighting as part of the robust regression and the pre-whitening as part of that auto-regressive filter applied to both sides of the equation. Epsilon comes out, with the proper properties. Just kind of a shorthand notation. We tend to use subscripts here to denote that it's the whitened weighted version. And so kind of if we look at, then we want to solve the model, we use this equation here, which solves for beta given the inverse of x times y. And then the covariance of that is given by this, where we have x transpose x inverted, and then sigma squared, which is the mean squared error of the residual from our model. And what we do when and this is this has the proper properties across time. It still has spatial covariance because that same physiology and stuff. While there's an innovation, we've moved its temporal history. It's still affecting multiple channels and stuff. So this when we go solve it, this ends up to be a channel. It has off diagonals in the channel by channel space, but it's modeled here. So we actually, I'm showing this equation just for one channel, but we actually do this to solve for all the channels, such that our beta covariance is both across all the different conditions and how the conditions vary with each other, but also has space kind of embedded into it. So it's the full covariance matrix. But this is how you would end up solving for beta and the covariance model. We're going to return to that spatial covariance much later when we start talking about group level and region of interest stuff. But we're actually propagating that all the way through here. And so if you wanted, again, why do I put stuff all at the bottom? If you wanted to then do a statistical test on this, let's see if I can just bring up that. Oh, no, I can't, because I have stuff above it. So if you want to do a statistical test on this, what you would do is you would define what's called a contrast factor. So we call it your C. It's the same notation that's used in AFNI or SPM. And so let's say you had two tests, left hand and right hand tapping. So you have, just in a simple model, you might have two betas. First beta is left, second beta is the right-hand tapping. And so if you wanted to compare left versus baseline, the contrast vector would be 1 and 0. And you multiply that contrast vector times your vector of betas. And then on the bottom, you sandwich the covariance in here so that you're able to account for the fact that maybe the left hand and the right hand tapping were not independent based on the timing of the design matrix. That non-independence is completely dictated by the design matrix. All right? If you wanted to compare, say, left hand to right hand, that contrast vector would now be something like negative or 1 and negative 1, because it's now going to subtract those and it's going to give you the effect, the studentized t-test, to compare the two different conditions. Okay? So that's how we take this output of betas and covariance and compute a t-score for it. Now, going back a little bit, there's actually two different variations that are used in NIRS in terms of the design of X. So I haven't really talked about what X is other than it encodes the stimulus events. So this is what's called an FIR model, which is a deconvolution. So in the deconvolution model, it's kind of like akin to ERP averaging, that basically what you're doing is you're estimating the hemodynamic response every single point. So you've got say a 30-second window, you want to estimate the whole response, you've got 30 seconds, let's make it easy, 1 hertz, so you've got 30 betas, and you're estimating all 30 of these betas, and your design matrix looks like this, that each column of it is, the first column is the stimulus onsets, and then it's the stimulus onsets shifted by 1 and 2 and 3 to generate a matrix that looks like this, which is shifted, and then use this for your X matrix, fit against there, and you get your betas, 30 betas or whatever, you can plot them out as a function of time, and you would see a response curve like this. You have to tilt your hands. So that's kind of this deconvolution. Historically, with the NIRS field, a lot of the early adapters to NIRS, especially in the pediatrics, were coming out of EEG labs, right? There's the first labs doing NIRS were all EEG labs, and they were very familiar with this style of, this idea of actually seeing the entire ERP type response. We call it an HRF, dynamic response curve. But it's so a lot of the early days in pediatric NIRS, we're seeing this. A little bit more recently, as we started to get the fMRI people kind of moving into the NIRS field, in fMRI, what they do is they typically use what are called canonical models. And the idea of a canonical model is, instead of estimating 30 betas, and then from those 30 betas having to do a second step of what window should I use for my brain activity. So computing statistics on here is a two-step process, right? You compute the 30 betas, and then you define your contrast vector down here. Say you wanted to use the window right in the middle, so that'd be 0, 0, 0, 1, 1, 1, 1, 1, 0, like that, and that's your contrast vector. And you compute then the contrast over a time window that way. So instead of that two-step process, what the fMRI people started to do was this idea of a canonical model, where instead of solving for the entire curve and then picking a window, to kind of go in with the hypothesis that I believe, based on hundreds of fMRI studies, my response looks like this. And basically what you do is you now compute a single beta, and that beta is the correlation between your data and this expected response. So you're directly testing the hypothesis, did my data look like that expected response? Okay? And so you get, in this case, in the canonical model, you predefine what the shape is. It can't be anything other than this. So looking at a time course doesn't make sense anymore. And you get one beta that encodes both the design and the hypothesis of what window you should be using. Okay? And historically in the NIRS community, again, we started off very much doing these methods. In recent years, programs like NIRS SPM and stuff started to introduce methods like this. We had a lot of pushback, let's say, from particularly the pediatric NIRS groups. that you hear the argument of, well, your fMRI canonical model was based on adults, right? No one has studied my population. I don't want to make those assumptions. I don't know that my response necessarily looks like that. And so we had a lot of arguments about which method was actually more appropriate, which method was better with your analysis. And so, oh, this is exactly what I just talked about. I should learn, to know what the next slide is. Anyway, so the two models, the canonical, you have one beta, widely used in fMRI, the deconvolution, you have multiple betas. This is what's implementing things like Homer 2. But it drives a two-step process. And there's the same slide that I showed. Okay. And do I have... Sorry, I'm gonna return to those two slides in a second after I finish my thought here. But it turns out that what you can think of is kind of exactly how I described it. That the canonical model is encoding both your stimulus events and directly encoding your hypothesis. So it turns out if you think about this equation, C times beta, and that's your t-square is C times beta, it's the product of two vectors. It's the inner product of two vectors. So the inner product of two vectors is going to be maximized when the vectors point in the same direction, right? So if beta is a time course that goes up and peaks at 6 seconds and comes back down, my C contrast, the maximized T, should also be tapered and peak at 6 seconds and come back down, right? And so in other words, it's actually, you'll get a better T-score, higher T-score, if you use a tapered window rather than zeros and ones as kind of a block. That's not what your shape looks like. That information, that response as it's building up at the early time points, it has information. It doesn't have zero information. It has some information, just not as much information as maybe the peak. So you should really be using a tapered window, okay? And so if you think about maximizing the T-score, the tapered window actually is better than a fixed, zeros and ones over a fixed window. And so what you can do is you can go and actually set those two equations equal to each other. And what you find is actually if you used a tapered window that was in fact the canonical response, you would get the same T-score as if you used the canonical response in the first place, at least if your noise is white. And there's a little bit of correction for design matrices, but for the most part, if your contrast vector was tapered like this, you would get the same T-score as if you used that model in the first place. So what that leads us to is the interpretation of a reinterpretation of the canonical model. Not as this is the one and only shape that my data is. It's encoding the hypothesis, right? And had I scanned infants and my infants had a different shape, and I'm able to maybe I don't find I fail to reject the null hypothesis, right? I don't find any activity, right? Had I used a different hypothesis, I might have found activity, right? It doesn't necessarily mean there's no activity there. It just means that I was unable to reject my null hypothesis. And so using the wrong canonical model on your data is the same effect as using the wrong window of time on your data. Okay? And so you can, and then we get into the argument of, well, if I do a deconvolution, I can look at the data and choose an optimal window and so on. Well, okay, well now you're taking the data, you're fitting your hypothesis to the data, so you're going to have false positives that way because you're basing it on the data. So we've really been pushing this idea of the canonical model is actually better than the deconvolution. I have a couple slides later on. I'm going to return to something and then go back to that. Because the canonical model has less degrees of freedom, and so it ends up actually be a bit more stable for non-ideal noise. But it actually ends up to be, you can interpret the canonical model in this way, that it's just really, it's what window I used. And if I used the wrong window, okay, maybe I didn't see activity, and had I used a different window, I might have. Okay, so let's go back 2 slides here, and this is just
Oops, come on, go back. Go back. Oh, go back too much.
So,
Yeah.
So it's well known that hemodynamic response function itself is different each individual.
Yeah.
And then some accounts by having putting more parameters to canonical.
Yes. So while my computer is thinking, apparently. So yeah. I mean, that's the slides I'm going to return to. I think in a bit, but yeah. I mean, let's say there's a couple problems with that. One is, yeah, my hemodynamic response might vary from subject to subject. Worse is that it varies systematically between two groups, which means that which is again using the wrong window. If I use a window from say 0 or say 2 to 8 seconds for Group A and Group B, but Group B was much more latent, I'm going to have lower effect sizes for that group, right? Your statistical test in terms of comparing those two groups, you were asking, were they different? Yeah, they were different. You just can't say it was due to amplitude, right? I used the same window for both. I found a difference in using that window. It just tells you the two groups were not the same. It doesn't tell you in what way they were actually different. So yeah, I mean, if you start thinking about what you're actually doing with the statistics in terms of how it's affected by those kind of systematic biases between, it's also the same thing if you look over space, that maybe my visual evoked response is different than my cognitive in terms of timing. And if I'm using the same window, I might have more sensitivity here than there. Same thing holds true with deoxyhemoglobin versus oxy. If I'm using the same window, then my deoxy I know to be shifted, I'm going to have lower effect size then. But it's so whether it's still a bit debated whether or not you use a canonical model that's tailored to that part of the brain or a different one for oxy versus deoxy. We're going to return to that in a couple slides though, but it's a very valid point. Come on. Jesus. I have to stop this program when I go to the actual. Where I was trying to go, you guys have the slides in front of you, was we ran, here they are, here, yay, stop, don't move. Okay, so we ran the same, anyway, block design, event-related design, so again, that same idea of running simulations. We ran it for both canonical and FIR models in both a longer duration task and a short duration rapid task. Same thing holds true in terms of our method outperforms the ordinary least squares no matter what the X matrix actually is, and that we have we kind of have this control of type 1 error in all cases. So in other words, we have an algorithm that doesn't really care so much about the design of the experiment. It's something that can be used kind of on all data, if it has motion or not. If it doesn't have physiology, it doesn't matter, just the R are it's not useful, but it doesn't hurt you. And so it's an algorithm that can kind of be blankly used on all your data sets. That's as opposed to the pre-filtering or the motion correction and stuff like that. If you have data that doesn't have motion artifacts and you apply a spline motion correction to it, it could actually make it really bad, right? Because it's so this can be applied kind of blindly to all data, and you get the control of the type 1 error. Assuming that the assumptions that I said we were violating, that we generalized the model to deal with, are the only things that were wrong with your data. And if you go to the case that you now have something else that's wrong with the data, like a systematic or a non-stationarity in the noise, or your physiology changes specifically during the task, you've still got some violations of the model. And we're going to see that again in